Okay, so in the last video, I feel like I kind of went really quickly and maybe glossed over this idea of the pKa and pKb. So I said that pKa was uh, sort of the strength of an acid. It's how readily an acid. So if we have some molecule, which I'll just represent as R, that has an OH on it, for instance, then the pKa was how readily this hydrogen ion was going to detach from this molecule. So we would end up with something like this. And this is, I mean, that's true, but there's more that can be said about it. And so I just wanted to show that there's this pKa table here. So pKa, whenever you see something in chemistry with a P before it like that, for instance, pH, then that equals the negative log of the concentration of hydrogen ions, and pKa is equal to the negative log of the Ka, which I said was the dissociation constant of an acid, of a hydrogen from its from the molecule that it's bonded to. And so here, there's just a list of these acid species, so you can see that they have these H's on them, which are the H's that become detached, and we have hydrochloric acid here, whereas pKa is -3 according to this table. Sulfuric acid, which is -3, and you see this is H2SO4, and then down here we run into HSO4, which is the pKa for that other hydrogen, like I talked about, which is 2. So the first hydrogen detaches with -3. Remember, the lower the number, the stronger the acid. So -3 for the first H, and then 2 for the second H. And we have some other acids here. Nitric acid is another one that you come across quite often in chemistry, and that has a pKa of 0. But the other thing I wanted to talk about here, which I neglected to talk about in the previous video, was this idea of the conjugate base and how that relates to the acid itself. And so the conjugate base uses this thing called the pKb, which is uh, which is the opposite of this pKa. So pKb is the negative log of the Kb, which is uh, which unlike this, which is the dissociation constant of hydrogen, the pKb is how much something like this actually wants to rebond with the H. And so with the pKa, you're taking the negative log of the Ka, which is the ratio of your acid species, which we can represent like that. That's the acid, and then the H that's coming off of it. So the A is this up here, and then the H is that. Because then the numerator, we have our products, which, so this right here was similar to this species here, where the H is still attached. And then up here we have this detached, and then this detached. And so this is how we calculate the Ka, where the Kb is uh, is our detached uh, our detached molecule here, or ion, which is called the conjugate base. So that's the conjugate base. It's conjugate to the acid. And then we have that. And then up here we have our HA, which is this conjugate base having taken back the hydrogen ion. And then right here we have the OH minus, so this is showing that it has taken a hydrogen off of water. So here maybe instead of a hydrogen ion we could have this, and it's taking this off of water. So this is how the Kb is represented. So that's the strength at which this species wants to extract hydrogen ions off of some other molecule. And we see up here, this shows sort of a one-to-one basis for all these. So we have our hydrochloric acid here, which is a pKa of -3, and then the chloride ion, which is what you get after the hydrogen detaches from it, has a pKb of 17. And pKb, just like pKa, works similar in that lower numbers are stronger. So a number of 17 is a pretty weak base. This isn't going to extract hydrogens, so we wouldn't have our chloride ion here. We have water, for instance, that should be a O. And this isn't going to extract hydrogens off of water very readily. It's a very weak base. And so we see that there's a relation here where if something is a strong acid, then it's a weak base. We see here that as we go down the table, our acids become weaker and weaker, but our conjugate bases become stronger and stronger. So there's an inverse relationship between our acids and their conjugate bases. And so something with a high or a low pKa rather is going to have a high pKb, and vice versa. If something has a high pKa, then it's going to have a lower pKb. And so if we want to, I said in the previous video that we have this Kw, which equals H3O plus, the concentration of H3O plus multiplied by OH minus. And we get this from from our K, that should be uppercase, Kw, and I said before, so yeah, this was what I defined it as, but where we get this from is we have Kw equals Ka times Kb, which then equals our H3O plus A minus. So this is just that equilibrium equation that I showed up here. We just plug that in for the Ka, since Ka equals this, and then HA, and then our Kb, which was this up here, so we multiply this by HA OH minus over A minus. Then you see this cancels out with this cancels out with this, and so we just end up with our H3O plus and our OH minus. And so we can take this idea here and actually convert it into KBs, and so this is the negative log of Kw equals the negative log of Ka times Kb. And if you know your logarithm rules, this can then be turned into the negative log of Ka plus the negative log of Kb. And so over here, the Kw, which I said was, the Kw was 1.0 times 10 to the negative 14. So if we take the negative log of that, what we end up with is 14, and that equals, so this is the pKa and this is the pKb, and so we end up with the pKa plus the pKb. And so if we add the pKa and pKb together, we will end up getting this, we will end up getting 14 every time. And so we can calculate a pKa from a pKb and vice versa. And so let's just run through that real quick. So if we have something that has a pKb of 17, then we subtract pKb from both sides, and we said that was 17. So 17, that's our pKb, equals pKa. 14 minus 17 equals negative 3, and we see that with our pKb of 17, we end up with negative 3, and so that's the pKa of hydrochloric acid. And one other thing we can do here with the pKa is we know that the pKa is equal to the negative log, and we said it was the negative log of Ka, which we also know is our conjugate base plus the concentration of our hydrogen ions, or up here we call it our hydronium, but hydronium is sort of equivalent to the concentration of hydrogen ions, because the hydrogen ion is the thing we're interested in up here. So these things are equivalent. And then that was over this species here where they're attached. And so we have our pKa equals this, and then we can, using our log rules, we can once again say pKa is equal to the negative log of A over HA, and our log rules, if you have a multiplication inside of your logarithm, then you can turn that into a plus logarithm. That will be plus negative log, because we're interested in the pKa's here. So that's plus a negative log of this. And I said before that negative log of hydrogen concentration is the pH. And so here we have pKa equals negative log of A over HA plus our pH. And so with this, if we add this to both sides and then just sort of flip the equation around, we end up with pH equals pKa plus the log of A over HA. And this is what's called the Henderson-Hasselbach Equation, or as I always seem to call it in my head, the David Hasselhoff equation, but it's called the Henderson-Hasselbach equation. And what we can see from this is, so one way to always remember which way this logarithm goes, or at least a shortcut I always remember, is A in the top, HA in the bottom. Aha! Aha, we have our logarithm. So that's a way to remember which concentration goes where. And we can think about how pH behaves in certain ways with this. So if our A species in the top is equal to this in the bottom, then we're at an equivalence point where we have half of these being dissociated and half of them being in the associated form. And if you have logarithm of 1, which if these are the same, then dividing them just makes it 1. And logarithm of 1 is equal to 0. And so if these are the same, then your pH is equal to your pKa. And so the pKa is sort of a measure of of like an average, maybe, where your pKa tells you sort of what around what pH your solution will be. If you add an acid of a certain pKa, then it's probably going to draw the solution closer to that pKa. So, for instance, if you have acetic acid, which was 4.75, it was a pKa, I think, of 4.75. So if you have water, which has a pH when it's neutral of 7, if you add our acetic acid to it, then you're going to pull this pH down, which makes it more acidic. It's not necessarily going to reach a pH of this, but you know that it's going to draw the pH towards this number. And so if you have a solution that's maybe at a pH of 1 and you add acetic acid, then it's probably going to draw it not as strongly, but it's going to draw it sort of in that direction. Well, maybe more accurately to say that if we add acetate, which is the acetic acid, the conjugate base of acetic acid, then it's going to draw it towards this pH of 4.75. And so we can understand pKa both as the strength of the acid, but also the number that is going to sort of draw the pH towards if you add it to a solution. And so what determines the strength of the pKa is how stable the conjugate base is. And so there's a lot of different ways that these can be stabilized, but one that I talked about before was our resonance stabilization. So if we have acetic acid like this, then it's stabilized because we can have this resonance stabilization where those electrons go there, those go there, then this has the negative charge. And so it's the charge which destabilizes the molecule is stabilized somewhat by this resonance stabilization, by this resonance structure. And so that's why our acetic acid, also known as vinegar, has this lower pKa. And when we talk about something like just a chloride ion, it doesn't have the resonance stabilization, but chloride ion has a fairly high electronegativity, and so it's more likely to be able to hold on to this electron and have a charge without having to grab onto something to neutralize it. And so there are lots of different ways that these conjugate bases can be stabilized, but just know that if something has a lower conjugate base, or a lower pKb rather, then it's more stable. So we see here ammonia, which is fairly alkaline or basic is our NH3, and that doesn't have any charge, which is why uh, this is somewhat stable. Um, but we see that it's also fairly basic. It's fairly alkaline. It has that lone pair there. Nitrogen is fairly electronegative. I think it was something like 3.0 for electronegativity. So it's going to want to grab onto something else. Uh, I'm not going to go too much into all the ways these can be stabilized because uh, it can it's just not really relevant. It's just relevant to know that if something has a low pKb, and we could end up having much stronger bases than this. Things that have like OH, which is the hydroxide ion. That's uh, a fairly common base that's used in things like sodium hydroxide and potassium hydroxide, magnesium hydroxide, things like that. That's sort of your quintessential base, and that will have a pKb. I don't know what it is offhand, but I'm almost certain that it would be in the negatives. So that would be a very strong base compared to these, where this isn't a table of bases. It's just showing the pKb of the various conjugate bases from these various acids here. And so these are all fairly weak bases, so they're stabilized in the form that they are without their hydrogen attached. And so, there are sort of chemical reasons like this why some acids are strong and some are not. For instance, why is it that if we have ethanol, why isn't that a strong acid even though it has this oxygen, hydrogen, and then acetic acid on the other hand, which just has this double bonded oxygen up here, different from this, is a much stronger acid. I don't remember the exact pKa of this, but I want to say it's something around maybe 18. It's in the teens, the mid-teens, I believe. And this we know is 4.75. And so we know that this has a pKa that's really high. So if we had it in its conjugate base form, it's likely going to have a pKb that's extremely low. So I said this was 18, so if that's true, I don't know exactly what it is, but if that were true, then our pKb would be 14 minus 18, which would be something like -4. So we see this is a very strong base. And so if it's in a solution of water, it's going to quickly snatch up this hydrogen here, and it's going to end up back as this species. So this is not a strong acid, where this is a fairly strong acid. Its conjugate base, oops, its conjugate base has a pKa, or a pKb rather, that's quite a bit higher. So if this is 4.75, then its pKb will be 9.25, which is pretty high. So if we have water here, it's not going to snatch those hydrogens up nearly as much. And so we end up with more of these hydrogens being detached and in solution, usually in the form of hydronium. Anyway, I think I've droned on long enough about this, but I just thought that in the previous video I didn't explain pKa and pKb very well, so I wanted to make sure that I went over that so that that became more clear. And so I will see you in the next video.